Okay, so I thought I would show an example of solving a 3 by 3 system of differential equations using the eigenvalue and eigenvector method. And I'll do this all the way, I'll show all the work, and yeah, parts of it will not be too pleasant, but we will survive. Um, Okay, so the first thing I do is I write down this matrix and I want to find the eigenvalues and the eigenvectors. Um, yeah, so I want to find the eigenvalues and eigenvectors of this matrix. So I have to find this determinant. This is a 3 by 3 determinant. I'm going to copy down this column and this column. And then I go down, 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 up, up, up. Okay, so here's the one I'm really afraid of. This times this times this. So let me take this slow. This times this, like it's the same as like lambda plus 1 times lambda plus 1 because I can cancel two negatives. So I'm going to write 2 minus lambda times, and then I'm going to go ahead and multiply this out. This is the same thing, right? This times this is this. So, and then obviously I have to do more work later to multiply that out, but okay. And then now this is just numbers, so this will be a plus 4, and this will be also a plus 4, I guess. Yeah, so I did down, 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 and then I go up, up, up. So this one would be negative 4 minus 4 lambda. This one would be also negative 4 minus 4 lambda, right? This one would just be a 2 minus lambda. So my total for the top is negative 6 minus 9 lambda. On the bottom, I've got what? I've got a negative lambda cubed. I should also have some lambda squared terms. Let's see, I've got a 2 lambda squared, but I would also have a negative 2 lambda squared when I did this times this. So it looks like I don't have any lambda squareds. So where are my lambdas? Well, I would have a 4 lambda from this 2 times 2 lambda. So I'd have a 4 lambda. I would also have a minus lambda from a 1 times minus lambda. So I would say 3 lambda. And then I would have a 2 because of 2 times 1. But then I would also have plus 8. So plus 10. I really hope I didn't make a mistake. This will be a nightmare if I made a mistake. Right, so the determinant is I do the bottom minus the top. Negative lambda cubed plus 12 lambda plus 16. And I'm setting that equal to 0 because the eigenvalues are when that determinant is 0. And yeah, I think so. So of course we have some guesses. Our guesses would be factors of 16. I can in my head, I can plug in lambda equals 1 and tell that that's not going to work. Lambda equals -1 is also not going to work. And I'm thinking about factors of 16. So, but I think 2 works. Does 2 work? Because this would be, no, 2 definitely doesn't work, because this would be a -8 plus 24 plus 16 is definitely not 0. What about, yeah, -2? Because if it was -2, this would be +8 minus 24 plus 16. Yeah. Okay, so what does this mean? First of all, I just ran a negative sign through here. And we believe that we know a root would be -2. And yeah, so I'm kind of glad this one turned out the way it is, because this is a great opportunity for me to remind everybody that there's a 0 here, because there's no lambda squared. You've got to be careful about this. It's very easy to miss the fact that there's no lambda squared here, but this will not work if I don't put the 0 where it's supposed to be. So I do my thing. That means it worked. We knew that it should work, but that's a good feeling. So this factors into lambda plus 2, because it's lambda minus -2, right? Times lambda squared minus 2 lambda minus 8. Oh, we got blurry. There we go. And now this should be much easier. I'm just factoring this. I can think of 2 numbers that multiply out to -8 and add up to -2. Those would be lambda plus 2 and lambda minus 4. All right. So I got a repeated eigenvalue of -2, and then just a regular eigenvalue of 4. Now I want the eigenvectors. Let me do lambda equals 4 first. This is where I go back to this matrix. I'm going to set up an equation with 0 on the right, and what's on the left is it's this matrix, but I subtract lambda down the diagonal. So -5, -1, 2, -1, -5, -2, 2, -2, -3. So I solve that. I would like a 1 here, so I'm gonna switch these 2 rows. But because I can, I can do more than one thing at once, I'm gonna also run a negative sign through this. So 1, 5, 2, 0. -5, -1, 2, 0, 2, -2, -3, 0. I'm going to do row 2 plus 5, row 1, row 3 minus 2, row 1, and that will give me 0, 24, 12, 0, 0, -12, 9. Wait. Is this, did I make a mistake? This is negative 12. Oh, yeah. Yep. When I did this, I was subtracting 4 down the diagonal. This should be a negative 2. And so this, yeah, this should be a negative 2. And so this should be a negative 2. And so this should be a negative 6. There we go. Yeah, I think this harkens back to another place when I made a mistake and I was able to realize why, because what am I doing? I'm finding an eigenvector. This matrix, the solution should not just be 0, 0, 0. In other words, when I'm solving this equation, I have to get a 0 row, unless I made a mistake. I have to get a 0 row. And I could already see that at this point, the third row should be a multiple of the second row, and now it is, but before it wasn't going to be, and that's how I knew I made a mistake. So where are we? This is slightly bad, but not that bad. I mean, I'm terrified of dividing by 24, but it's not going to be that bad because I mean, the worst fraction is a half, and as far as fractions go, a half is not that bad. So I'm here, and I'm about to do row 3 plus 12 row 2, which of course is going to zero out the bottom row. Oh, and yeah, by the way, it would be smart if I also did row 1 minus 5 row 2 to get this in reduced row echelon form. So I would go 1, 0, oh, and now I have to mess with fractions. 2 minus 5 halves would be negative 1 half. And of course, the bottom row is now zeroed out completely. And yeah, so we're there. This one's free. So I would do x3 is t, x1 would be 1/2 t, x2 would be negative 1/2 t. So then I get the vector 1/2 t, negative 1/2 t, t. Of course, I just want one eigenvector as far as I'm concerned here. If I wanted a basis for the eigenspace, I would pull the t out and get this one vector, and I would call that the basis for the eigenspace. I don't really care about all eigenvectors for this. I just want one eigenvector. So plugging in t equals 1 is good enough. Again, don't put in t equals 0 because 0 is never considered an eigenvector, but putting in anything else should be fine. So I'm just going to go, well, okay. Let's do t equals 2 because I hate fractions. So 1, negative 1, 2. Okay. Still need to find eigenvectors for the other one. Let me get another sheet of paper. this will actually be easier doing -2. -2 is the repeated eigenvalue. So this actually should be easier because the resulting matrix, because I'm going to do the same thing, I'm going to subtract down the diagonal, and the resulting matrix should have rank 1, meaning we should see, I'm talking too much and then I'm going to mess myself up. So I'm adding 2 down the diagonal because I'm subtracting -2. But what I was trying to say is we should see immediately that this matrix is it's a singular matrix, and in the sense that actually both the second and the third rows are multiples of the first row. Like the second row is just if I ran a negative sign through the first row, and then the last row is if I just took the first row and multiplied it by 2. This is a rank 1 matrix, meaning that there's essentially just one there's one essential row. The first row is essential, and the second and third rows are just multiples of the first row. What I can do is I can zero these out. I mean, if I run through the standard procedure to get this in reduced row echelon form, immediately I'm going to zero out the second and third row. It's very easy. And then, oops, sorry, I went a little off screen here, but this is free, this is free. So say x2 is s, x3 is t, x1, I solve for it, it would be s minus 2t. I put these in a vector. I can do my s part and my t part. And right, what's going to happen, these two are a basis for my eigenspace. Of course, the question here wasn't to find a basis of the eigenspace, but that's what these would be. As far as I'm concerned for this, I just wanted 2 eigenvectors because this is an eigenvalue that was repeated twice. Of course, there's always the possibility that I'll have a defective matrix and then the geometric multiplicity would be less than the algebraic multiplicity. I'm not going to give you an example like that. If you have a repeated eigenvalue, you will find that many eigenvectors. So we had an eigenvalue that was repeated twice, and we found 2. So I think we're basically done here. Once you find the eigenvalues and eigenvectors, you're basically good as long as you know how to assemble your answer. If you remember, this all came from a system of differential equations, and we were using the eigenvalue and eigenvector method to use it. Of course, you should also know what happens when you get complex eigenvalues. So you should review that, but that isn't what happened for us. We got real eigenvalues. So I'm just going to do what you do for that. Basically, it's e to the eigenvalue times t. So let's do the eigenvalue 4. Times the corresponding eigenvector. And the eigenvector for 4 was this one. times some constant plus, and then I'm going to have C2 times, okay, now I do the next e to the next eigenvalue, so e to the negative 2t, and I'll pick one of those eigenvectors, and then I should have a C3, and again, because this eigenvalue was repeated, I need to repeat this one with its other eigenvector. And that's it. You just need to know how to put your answer together. And yeah, the truth is it's not that different if you have complex eigenvalues. It's just a different formula. It's the one involving sines and cosines, but the final is going to be open book. And I know that formula is a bit tough to remember. The truth is I don't memorize it by heart. I just use it when I need it. So anyway, you know where that one is, and it isn't all that different. So yeah, I will upload this video.